Right now, at this very moment, there are galaxies being erased from our universe, not destroyed. Erased from our ability to ever observe them again. This is happening in real time, and it's been happening for billions of years, and it will accelerate until eventually, in the distant future, nearly everything we see in the night sky today will simply vanish beyond our cosmic horizon forever. But that's not even the shocking part. The shocking part is what happened just last year, when the James Webb Space Telescope looked at a region of space that humanity had already studied thoroughly with our best instruments. A region we thought we understood. A region that was supposed to be relatively empty. And it found something so massive, so densely populated, so absolutely staggering in its scale, that it forced astronomers around the world to admit that everything, literally everything, we thought we knew about how the universe works is incomplete. Here's what Webb discovered in that single patch of sky. Nearly 800,000 galaxies, in an area so small you could cover it with your hand. But the number isn't the shock, the number is just the headline. The real shock is what that number reveals about everything we were blind to. Because for decades, we thought we had already seen that region. We had already cataloged it. We had already built our entire understanding of the cosmos around what we thought was there. And we were measuring only 1/10 of 1% of what was actually there. Let me show you what that means. And why this discovery has triggered an absolute crisis in cosmology. Because this isn't just about galaxies. This is about our entire understanding of cosmic history. This is about the impossibility of what Webb keeps finding. This is about the window closing on humanity's ability to ever understand the universe in this way again. To understand why this number is so absolutely stunning to the scientific community, you need to understand what the previous baseline was. You need to know what we found when we looked at essentially the same region of space using the best tools we had available before Webb arrived. In 2004, NASA released an image from the Hubble Space Telescope. This image is one of the most famous scientific photographs in history. It's been reproduced in textbooks, it's been displayed in museums, it's been studied and analyzed and celebrated by the scientific community for more than 2 decades. This image was called the Hubble Ultra Deep Field, and it showed us something revolutionary. It showed us that when Hubble pointed its cameras at a region of sky roughly the size of a grain of sand held at arm's length, it could detect approximately 10,000 galaxies. 10,000 galaxies. Think about that for a moment. Hubble was considered the most powerful observatory in human history. It had revolutionized our understanding of the cosmos, and it found 10,000 galaxies in that tiny patch of sky. The image was celebrated as a triumph of human engineering and scientific achievement. Textbooks were written using Hubble's data as the foundation. Cosmological models were calibrated to Hubble's observations. Our entire picture of the universe, how densely populated it was, how galaxies were distributed, how the cosmic web was structured, was built on what Hubble could show us. Scientists were satisfied. Not completely satisfied. There's always more to discover. But satisfied enough that we had captured an essentially accurate picture of the deep universe. We were confident in our understanding. We were wrong. When the James Webb Space Telescope pointed its infrared instruments at comparable regions of space, studying the same deep regions of cosmic history that Hubble had already examined, it found something that shattered that confidence entirely. In that same patch of sky, Webb didn't find 10,000 galaxies. It found 800,000 galaxies. That's 80 times more galaxies than Hubble detected. That's not an incremental improvement. That's not a 50% increase or even a 200% increase. That's 80 times as many galaxies. That's a complete categorical difference in scale. One of the leading researchers on this project, physicist Caitlin Casey from UC Santa Barbara, who co-leads the Cosmos Web project, described the scale difference in a way that makes the magnitude absolutely clear. She said, if you printed the Hubble Ultra Deep Field image, the one celebrated as humanity's deepest view of the universe, on a standard piece of paper, the Webb image at the same depth would need to be printed as a mural. A mural 13 feet wide and 13 feet tall. Imagine holding that paper image in one hand, then imagine the mural taking up an entire wall. That's the difference. That's what Webb revealed when it looked at the same region of space with instruments tuned to wavelengths that Hubble simply couldn't detect. The Cosmos Webb image isn't just 80 times larger. It's 10 times denser with detected structure than our best models predicted it should be at equivalent depth. 10 times. Not 10% more. Not twice as many. 10 times more galaxies than our most sophisticated predictions anticipated. This is the moment when you have to understand what we're actually dealing with. This correction, this massive, undeniable upward revision of the galaxy count, this is not a refinement of what we previously understood. This is the collapse of a framework. This is a revolution in how we understand the fundamental structure of the cosmos. Now here's the critical question that follows naturally from this revelation. If these 800,000 galaxies were there all along, if they existed in the region of space that Hubble had already studied, then why did we miss them? Why did the best space telescope in history look at this patch of sky and see only 10,000 galaxies when there were actually 800,000 waiting to be discovered? The answer to that question isn't mysterious once you understand the underlying physics. It's elegant, actually. It demonstrates a fundamental principle of how light behaves when it travels across an expanding universe. When the universe expanded after the Big Bang, it didn't just move things apart. Space itself expanded. The fabric of space-time stretched. And as space stretched, everything traveling through it, including light, got stretched along with it. This process is called redshift, and it's crucial to understanding why galaxies were hidden from our previous generation of instruments. When light from ancient, distant galaxies travels through expanding space for billions of years, that light gets stretched progressively toward longer and longer wavelengths. It gets pulled away from the visible spectrum that human eyes can detect toward infrared wavelengths, heat radiation that's completely invisible to our eyes, and that, until Webb, was essentially invisible to our best space telescopes as well. Visible light, the light that telescopes like Hubble were optimized to capture, gets progressively shifted toward infrared wavelengths by this cosmic stretching process. The deeper back in time you look, the more stretched the light becomes, and the farther it shifts into infrared and deep infrared territory. Hubble was built to see visible light and near ultraviolet light. It could detect some near infrared wavelengths, but it couldn't hear the deep infrared frequencies where the most ancient and distant galaxies, the ones from the earliest periods of cosmic history, had their light shifted by billions of years of cosmic expansion. Those galaxies weren't absent from the data because they didn't exist. They were absent because Hubble's instruments simply couldn't detect the frequency they were broadcasting on. They were like radio stations, transmitting on a frequency that your radio wasn't built to receive. The James Webb Space Telescope was designed from the ground up with an entirely different approach. It was designed specifically to hear exactly those deep infrared frequencies. Its 18 gold-coated beryllium mirror segments span 6.5 meters across and collect more than 6 times as much light as Hubble's primary mirror. Its infrared instruments are sensitive to wavelengths that Hubble could never reach. When those infrared instruments were pointed at regions that previous surveys had found relatively sparse, regions where Hubble had already looked and cataloged as containing fewer galaxies, the darkness overflowed with structure. Galaxies appeared everywhere. Galaxies that had been invisible for decades. Galaxies that had been waiting patiently in the data, hidden behind a veil of light that our previous instruments simply lacked the capability to penetrate. This is the philosophical significance of what Webb has accomplished. The universe wasn't misunderstood because the data was wrong. It wasn't misunderstood because scientists were incompetent. It was misunderstood because the instruments available to us were capturing only a thin, visible slice of reality. Every deep field survey ever taken before Webb. Every galaxy catalog. Every cosmological simulation calibrated to observational data. All of it was built on a picture of the universe that was missing the majority of its early population. We were navigating by a map that showed only one continent while 9 others existed in the darkness beyond our ability to see them. When researchers at UC Riverside published the most detailed cosmic Webb map in May 2026, they described the jump in depth and resolution from Hubble to Webb, using language that emphasizes just how revolutionary this shift is. They noted that the cosmic Webb, the vast, invisible skeleton of dark matter, filaments, and sheets that connects galaxies across all of space, can now be traced with clarity all the way back to when the universe was only a few hundred million years old. That era was essentially out of reach before Webb. It was beyond our observational horizon. It was the cosmic dark ages from our perspective. The cosmic Webb that astronomers had been modeling for decades, building their understanding based on what Hubble could show them, was a smoothed-over approximation of a far more complex and far more detailed reality. It was like trying to understand the structure of a forest by looking at shadows cast on a wall. You get a general sense of structure, but you miss the intricate details. You miss the interconnected branches. You miss the true architecture of what's actually there. Webb isn't showing us a corrected version of that old picture. It's not showing us a refined version. It's showing us the actual picture for the first time. The cosmic Webb is more complex than we imagined. The density of structure is higher than our models predicted. The connections between galaxies in the early universe are more intricate and more established than theory suggested was possible. This realization alone would be scientifically significant. But it's only the beginning of what makes Webb's accumulated findings so genuinely unsettling to the scientific community. Alongside the sheer number of previously invisible galaxies, Webb has been systematically delivering a second discovery that's been generating increasingly urgent scientific debate since its first results emerged in 2025. The galaxies that Webb is finding in the earliest periods of cosmic history, galaxies from the first 300 million to the first billion years after the Big Bang, look nothing like what our accepted models predict they should look like at those ages. Our standard model of cosmology, called lambda, cold, dark matter, or lambda CDM, describes a universe that begins with nearly uniform hydrogen and helium gas. According to this model, structure builds slowly and progressively through gravity. Gas collapses into stars. Stars form into small, irregular galaxies. These small galaxies grow gradually over billions of years through mergers with other galaxies and through the accretion of gas clouds. Eventually, over cosmic time, these small irregular systems merge and interact until they become the large, structured spiral and elliptical galaxies we see in the modern universe. This model makes specific quantitative predictions. It predicts the mass that galaxies should have at each stage of cosmic history. It predicts their brightness. It predicts their structural complexity. It makes testable, falsifiable claims about what we should see when we look back at the early universe. Webb keeps finding galaxies that violate those predictions. In the summer of 2025, Webb confirmed a galaxy cataloged as JADE GS0140. This galaxy is remarkable because redshift analysis places it at just 300 million years after the Big Bang. It's one of the earliest galaxies we've ever observed. According to our models, this galaxy should be a small, dim, irregular smudge. It should be a formless collection of young stars just beginning to organize into something resembling a galaxy. It should be barely luminous. It should be structurally simple, but it's not. JADE GS0140 is spatially resolved, which means it has measurable physical structure. It's not a formless blur, it's an actual organized system. It's extremely luminous in ultraviolet light, which means it contains large numbers of massive, energetic stars burning hot and bright. And here's the detail that really troubles physicists. Spectroscopic analysis reveals the presence of heavier chemical elements, including oxygen. Oxygen can only be produced inside stars through nuclear fusion. It can only appear in a galaxy if entire generations of massive stars have already been burned through their nuclear fuel and exploded as supernovae, scattering that material back into the gas clouds that form the next generation of stars. For a galaxy to contain measurable amounts of oxygen just 300 million years after the Big Bang, entire cycles of stellar evolution must have already completed. Stars must have been born, lived, and died and distributed their material to create new stars multiple times over. The timeline implied by what Webb observed in JADE GS0140 is tighter than the lambda CDM model comfortably accommodates. The math doesn't work if you stick to the model's assumptions about how quickly stars can form and how efficiently the early universe can assemble stellar mass. But JADE GS0140 is not an isolated anomaly. In January 2026, astronomers at Texas A&M University reported a Webb observation that's even more impossible to explain within the standard framework. At least 5 galaxies in active collision with each other, just 800 million years after the Big Bang. These aren't isolated systems gently interacting at the edges. They're galaxies in direct collision, violent merger events. And this level of galactic organization and collision frequency, so early in cosmic history, was not predicted to be typical by the standard model. Here's what's critical to understand. These findings have not broken cosmology. That distinction matters. No peer-reviewed consensus has formed around the claim that the standard model is completely wrong. The field hasn't undergone a paradigm shift where everything is rejected and a new theory installed. What has formed is something more serious in a scientific sense, a growing body of evidence that the standard model's predictions about the early universe require either significant revision or entirely new physics to accommodate what Webb is actually observing. Some astrophysicists propose that star formation in the early universe was dramatically more efficient than the models predict. The theory suggests that the universe was converting available gas into stars at rates far higher than lambda CDM assumes. Others point to possible roles for dark matter behavior in the early universe that current models do not capture accurately. Dark matter interactions might have been different in the early cosmos. They might have assisted galaxy formation or stellar assembly in ways that our current understanding doesn't account for. A smaller group of physicists argues that the findings hint at something genuinely new at the level of fundamental cosmology. They suggest that Webb is detecting signatures of physics beyond the standard model. The scientific community is working through these possibilities methodically. Webb is generating new data to test these hypotheses every month. New observations, new confirmations, new anomalies. But the central fact is established and undeniable. The early universe looks nothing like what we predicted it would look like before we could actually see it at Webb's resolution. The theory that was built on incomplete observations, on what Hubble could show us and nothing more, has come face to face with observations that are no longer incomplete. And the theory has to grow to fit those observations. That's how science works. But it also means that our understanding of fundamental cosmic processes is less complete than we believed it to be. Now I want to walk you through perhaps the most significant dimension of what Webb has confirmed, the one that requires sitting in the darkness and silence for a moment before it lands properly on your mind. The universe that Webb is revealing as densely populated and as structurally complex as it's turning out to be, that universe is not the whole universe. It's not even the majority of the universe. It's the fraction of the universe from which light has had enough time to reach us since the Big Bang occurred 13.8 billion years ago. That's the observable universe. That's our cosmic prison of perception. The observable universe is defined by a specific boundary called the cosmological horizon, or the photon horizon. This boundary exists at approximately 46.5 billion light years in every direction from Earth. That number is actually larger than 13.8 billion light years, which is the age of the universe. And the reason for that discrepancy is crucial to understanding cosmic geometry. Space itself has been expanding continuously since the Big Bang. While ancient light was traveling through the universe for billions of years to reach us, the space containing it was stretching and expanding. That expansion carried the sources of that ancient light much, much farther away than the travel time alone would suggest. A galaxy whose light has been traveling for 13.2 billion years, one of the oldest observations we have, is now estimated to be approximately 33.8 billion light years away from us. That additional distance wasn't traversed by the light. That distance was created by the expansion of space during the light's journey. The cosmological horizon sits at 46 billion light years in every direction. But beyond that horizon, the universe almost certainly continues. How far it continues is a question that cosmology cannot currently answer from within its own observational limits. Cosmic inflation theory, the physics that describes the period of extraordinary rapid expansion in the first fractions of a second after the Big Bang, would have stretched space to dimensions far larger than our observable bubble, regardless of what the local geometry suggests. Some cosmological frameworks suggest the true universe is hundreds of times larger than the observable portion. Others suggest it's effectively without boundary. Some models propose infinite extension. The honest answer is that the observable universe is not a map of all that exists. It's a map of all that we can possibly perceive, given the constraints of light speed and cosmic expansion. Nothing that Webb can observe will ever change that fundamental epistemic situation. It's built into the physics. It's built into the speed of light. It's built into the geometry of space itself. But here's the dimension of this entire situation that is genuinely difficult to absorb emotionally, intellectually, and philosophically. The observable universe is not static. It's not a fixed boundary that will remain at 46 billion light years forever. It's actively shrinking in terms of what it contains. Dark energy, and the mysterious force that constitutes approximately 68% of all energy content in the universe, is accelerating the expansion of space. This effect was confirmed again by independent measurements published in June 2026 using corrected supernova data. Dark energy is real. It's driving cosmic expansion, and it's driving that expansion at an increasing rate. As a result of this acceleration, distant galaxies that are currently observable are being carried away from us at ever-increasing velocities. Let me emphasize this. Some of the galaxies that Webb observes right now are already receding from Earth faster than light can travel. This doesn't violate Einstein's theory. Nothing is traveling faster than light through space. Rather, space itself is expanding so rapidly that galaxies are being carried apart faster than light can travel. It's the expansion of space itself that exceeds light speed, not motion through space. But the practical consequence is profound. Any signal those distant galaxies transmit today will never reach us. Their light is being carried away by expansion faster than it can travel toward us. Those galaxies are already beyond our causal reach, even though we can still see them. These galaxies are observable only because the light currently arriving from them left those systems billions of years ago, when the expanding space between us hadn't yet grown fast enough to prevent their ancient photons from making the crossing. But those ancient photons already in transit for billions of years will be the last ones we ever receive from those galaxies. The light being emitted by those distant galaxies today is being carried away by expansion at velocities that exceed the speed at which light can travel toward us. It will never arrive. We will never receive it. Imagine a future civilization studying astronomy tens of billions or hundreds of billions of years from now. Imagine them looking upward at their night sky. What will they see? Not what we see. Not even a reduced version of what we see. A nearly empty universe. The accelerating expansion driven by dark energy will eventually push nearly every galaxy beyond our local group, out of our observable reach forever. The cosmological event horizon, the boundary beyond which nothing can ever reach us again, will eventually stabilize at approximately 60 billion light years. But by the time that stabilization occurs, the vast majority of the galaxies we currently observe will have crossed beyond that horizon permanently. The vast majority of the galaxies we currently observe will have crossed beyond that horizon permanently. The cosmic microwave background radiation, the faint afterglow of the Big Bang that current instruments detect, as a uniform glow of ancient heat radiation, will have redshifted so severely that its energy will fall below any conceivable detection threshold. It will be unobservable. The large-scale structure of galaxy filaments that Webb is now mapping in unprecedented clarity will be completely invisible. Its constituent galaxies will have been carried far beyond the event horizon. That future civilization will have no observational evidence of the Big Bang. They will have no visible galactic web. They will have no way to determine from the sky above them how enormous the cosmos actually is. They will have no evidence of cosmic structure spanning billions of light years. They will live in what they perceive as a cosmically isolated remnant of a universe that is, from their perspective, essentially empty. And they will have no way of knowing what they have lost access to. They won't even know that they've lost anything. A brief, shining era of cosmic visibility will have ended before their civilization even begins. Which brings us to perhaps the most significant realization that emerges from all of this. Right now, in this specific era of cosmic history, we live in a cosmically privileged moment of visibility that has no equal. The universe is structured enough, it's bright enough, it's accessible enough that a sufficiently capable telescope can read back nearly its entire history. Webb is that telescope. We are living in one of the last eras in cosmic time when so much of the cosmic record is still visible at all. The universe will not always be this legible. The window of observation is open right now, and it is closing. The Cosmos Webb data collected by Webb is available to any researcher in the world. The catalog of nearly 800,000 galaxies, spanning almost all of cosmic time, is publicly released. The Cosmic Web Map tracing the largest structures in the universe back to its first billion years is published and documented. The impossible galaxies of the early universe are cataloged and under active scientific investigation. What Webb is accumulating is not just data for professional astronomers. It is the most comprehensive reading of the cosmic record that any intelligence has ever attempted during one of the last eras in which so much of that record is still visible at all. Webb is floating in its precise gravitational balance point 1.5 million kilometers from Earth. It's reading everything it can reach before the expansion of space carries any more of it beyond the edge of what light can ever bridge. What comes after the observable horizon? What fills the universe beyond the last light that will ever reach us? What is the total scale of everything that exists actually amounts to? These are questions that no instrument will ever answer from within our cosmic bubble. These are questions that may be fundamentally unanswerable given the physics we live within. The universe is not just bigger than we thought when we based our understanding on Hubble's observations. The universe is not just bigger than we thought when we based our understanding on Hubble's observations. It is bigger than observation can ever confirm. Webb has shown us the true scale of the part we can reach. It's revealed the hidden 90% of the nearby galaxy population. It's demonstrated that our models of the early universe require revision. But it has also reminded us of something humbler and more profound. We live in a cosmos that extends far beyond what any instrument can ever measure. We observe a bubble of light in an infinite darkness. That bubble is vast beyond human comprehension, but it remains a bubble nonetheless. The 800,000 galaxies that Webb detected in a patch of sky smaller than 3 full moons is not just a number. It's not just a catalog entry or a data point. It's a reminder that our universe is far more complex, far more populated, and far more dynamic than our previous understanding allowed us to perceive. It's a demonstration that the limitations of our instruments define the limitations of our knowledge. It's evidence that science advances not just through better ideas, but through better eyes with which to see. The universe will not always be this legible. Right now, in this era, Webb is reading everything it can reach, every 800,000 galaxies in those tiny patches of sky, every distant structure tracing back to the first few 100 million years after the Big Bang. Every piece of data is precious because every piece of data represents something that future observers will never see. That's the real shock that the James Webb Space Telescope has revealed. Not just that the universe is bigger than we thought, but that we are living in one of the last moments in cosmic time when we can actually see just how big it is.